So thank you everybody for coming. I see a lot of either fresh or less like newish faces, so that's really cool. That means we've got a good topic. I'm really excited about this one. I really appreciate Nishant this up through our sign up sheet here and offering to come talk to us about this. So it's a Go meetup for 1st of November. Go actually act through here. One quick disclaimer about the room and the audio visual setup here. You don't see the mics, but they're everywhere. They're these little square things, and they will zero in on you even when you're whispering, and especially when you're whispering. So it is being recorded. Everything's being recorded here, and while we're not intending to record everybody's conversations, the room will just do it in an effort to pick up what people are saying. So be aware of that. There's all these links along the bottom of the slides. I would encourage you specifically to join the Forge Utah Slack, because that's where all the fun stuff happens, the salt and else that we like to talk about on there. Specifically, I always call out the jobs and hiring channels there. I think I actually just posted a massive still. So that's coming through. I know that there's people and a lot of change going on, but that's a pretty great place to recruit people, just meetups themselves. If you want to speak, just like Nishant, you can go to our paper call and create a submission. And it says it's for women who go Utah, but it was this meetup and that meetup combined a while back, so we still use this paper call, but it does allow you to come present here. We have somebody for December, but I'm basically wide open for all of next year. We tend to not skip, depending on exactly how close our January meetup is. We tend to not skip it. Sometimes it falls right next to New Year's and we'll skip it, but I think it doesn't this year. So I'd love to have somebody talk about whatever and submit there. And if you don't want to submit there, you want to do something that's formal, you can always hit either myself or Mariah at the channel, the Go Lang channel, and say, I want to speak at the Go meetup, and we can kind of work through it. So it doesn't have to be super formal. And that's it. That's all my boilerplate housekeeping stuff. I am going to hand it over to Nishant, who is going to talk to us about Heap optimizations. So go ahead, Nishant, and thanks again. Really appreciate you just picking us up.
Yeah, thanks so much. Wish I could have been there in person. Hopefully for the next one.
Yeah, for sure.
This is actually the first one of these that I've seen actually people getting together in person. I've done, I think this is my 4th Go meetup so far, and they've all been fully virtual. So glad you guys are together.
Yeah, we have a nice hybrid situation, and it's working out well.
One of the few London's getting together,
and
I think Berlin's getting together. I haven't seen that many in the U.S.
Yeah, San Francisco is definitely not getting together yet, but I think they were talking about wanting to start doing them in person. I think starting in
San
the spring.
Francisco organizer.
What was that?
The organizer of the meetup, Ari Waller, is in
Mhm.
Georgia.
Oh, maybe I'm thinking of a different one then. Maybe I'm thinking of Baltimore.
Anyway,
Well, we'll see. Hopefully I can come by and
They
see
should.
you all in Salt Lake City sometime. Cool, let me get started. So I'm here today to talk about heap optimization for Go systems, which was about 6 months of my life at Pinterest at one point. For a little bit of context, I've been at Pinterest for 5 years now. Started as a new grad, and now I'm leading the Pinterest ad serving platform team, which is a team that I've always been on. Our scope and size has changed tremendously over time. So when I first interned at Pinterest, all of ads infrastructure was 10 people, including 2 of us interns. Now all of ads infra is around 90 people. My team itself is 15. So it's been an interesting journey, to say the least. What my team does is now we're responsible for all the infrastructure that powers ad delivery. So every single ad that you see as a pinner when you go to the platform goes through our system. Pretty cool place to be, since we power every single dollar that the company makes in revenue. As a result, having to solve a lot of performance-intensive problems. The other interesting part about us is that we're the only online system at Pinterest that's written in Go. So there's not a lot of company-wide support today. We do a lot of our own performance tuning, general Go build support, et cetera, et cetera. So a lot of folks on the team have a lot of cool discovery to share about Go, and perhaps some other folks from the team can come by and share more of what they worked on over the years. So I'll get started with a quick intro to memory management itself and how it works in Go. At a high level, when I refer to memory management, I'm talking about the process of allocating memory for a program when you need it and releasing it for other programs when your program no longer needs it. The great part about Go is that all this is automated. Users don't have to perform manual memory management, so they don't need to manually allocate and clear memory. It's all abstracted away from you. The goal of this is to minimize the chance of memory leaks. And essentially the way Go does this, it has a garbage collector that runs every time the heap hits a certain target size. I believe there's a new setting in Go 1.19 that allows you to tune Go GC more with more granularity than before. But essentially, by default, when the heap grows by 100%, since the last time the garbage collector ran, the garbage collector will run again. This is configurable now. And the way the garbage collector works is it's a concurrent algorithm. So it uses a tricolor algorithm to first mark everything on the heap to determine what can be removed and what cannot. So it divides objects into 3 sets, therefore tricolor. The white objects are ones that are collectible since they are no longer in use in memory. Black objects are ones that are not collectible since they are definitely in use in memory. And the gray objects are ones that may be collectible that hasn't been determined by the garbage collector yet. So by doing this in the background, the mark phase of the garbage collection can run concurrently with the main program without requiring a stop the world pause, similar to what, let's say, old versions of the Java garbage collector needed. So then the question is, how does this impact our program's performance? First off, the Go garbage collector aims to utilize no more than 25% of your system resources, of your CPU resources. The goal again here being to minimize the impact on your program's performance. However, when memory pressure is high, the garbage collector does start to steal resources from your main program. And this is where it can start to really hinder the performance of your program, which typically manifests in the form of latency, et cetera. So what I mean by this is if the rate of memory allocation of your main program is really high, the garbage collector needs to be running more frequently and more aggressively. So it starts to steal Go routines from the main program to assist with this marking phase that we just discussed. And this does 2 things. One, it ensures that you're cleaning up as fast as possible. Garbage collector gets more power. Secondly, it also lowers the rate of memory allocation from your main program, since by default, by definition, by having fewer threads, your main program runs slower and allocates memory slower. So this acts as kind of a check to ensure that the rate of memory allocation doesn't exceed the rate of memory cleanup, which prevents the heap from growing to be very large, preventing out-of-memory errors, et cetera. So what specifically causes the garbage collector to run slower? So like we said, to determine what memory can be cleared up, the garbage collector needs to scan every single object in the heap and mark it as one of the 3 colors. So as the number of objects in the heap grows, the amount of time spent scanning the heap grows as well. So then the question is, what actually goes on the heap? And that's a huge topic, but at a high level, there's 2 areas for memory allocation, the stack and the heap. Stack is a special area of the computer's memory which stores all temporary variables created by a function that live only within the scope of that function. So once the function stack is cleared, those variables are no longer accessible. Therefore, if any variable within that function needs to be accessed later beyond the scope of just that method or that function, the Go runtime stores those particular objects on the heap. The heap is sort of a more free-floating memory region for global variables or any of these variables that are referenced beyond the scope of a single method call. And the way Go does that is through something called escape analysis. Essentially, if an object is only referenced within the scope of a certain call, the Go runtime determines it can be allocated to the stack. If not, if it's unclear, it'll just allocate it to the heap, knowing that the garbage collector can then clear it off later on, but it is accessible if needed. So in conclusion, number of heap objects goes up, time spent on marking the heap goes up, garbage collector runs slower, slows down your main program. So then how do you start to figure out if the garbage collector is what is impacting your system? And the first step is sort of intuition. So typically garbage collector pressure manifests in the form of high tail latency. And what I mean by this is if you think of latency as, or request latency as a percentile, for example, for a Pinterest system, obviously we're serving hundreds of thousands of requests per second. Each request will have its own unique latency number. We track those and track them at a P50, P90, P99 level. Once you start to see abnormally high latency values at high percentiles, like for P99, for instance, we were seeing sort of 100 millisecond spikes in a system that typically runs within 150 to 250 milliseconds. So that was sort of an intuitive guess that GC pressure could be the root cause here, especially because we knew that our program does have pretty high memory usage since we were storing a lot of data on the heap itself. So now that we had this hypothesis, how do we actually go ahead and confirm it? And there's a couple tools or a couple ways that Go allows you to do that. What we did is essentially leverage this Go runtime environment variable called Go debug. By setting Go debug equals GC trace equals 1 when you run your binary, you can force your program to output debug logs for every single GC cycle, which includes the time spent on the various phases of the garbage collection itself. So once that is printed, you can have it just pipe to standard error. Once that is printed out, then you can try and align the start and end times of garbage collection with your system metrics. For example, we use latency. So essentially, we just had this background thread that was printing out P90 latency for a single host that it was measuring locally itself. At the same time, this Go debug variable was printing out when GC was complete. And we could very clearly see that there was an alignment between latency spikes and when Go debug was printing out details about a GC cycle. So this is what GC trace's output looks like with an explanation of every single component in there. I'm not going to dive through every single one of them, but essentially we can see that it gives us a lot of information like how many GC cycles we've had so far, how much of our system's total CPU has been spent on garbage collection, how much wall clock, how much CPU time was spent in sort of each phase of GC, et cetera, and what our memory usage looks like before and after the objects were marked. If you want to learn more about this, you can just Google GC Trace and Arden Labs. I'll update the slides to have a link in here when I send it over. But there's a great post explaining exactly how all of this works. So like I said, what we did is we let GC Trace run, printed out our system metrics, and looked for correlation between GC cycles and latency or CPU degradations. So now that we concluded that GC was definitely our problem, and from our reading, from our learning, we knew that this typically only becomes a problem when there's a large number of objects in the heap. We knew that we needed to profile our heap usage, understand exactly what was on the heap, and where we had room for some optimization. So Go has a lot of cool built-in tools to investigate performance issues of various kinds. These are two that I found really helpful when debugging heap usage specifically. One was the runtime.memstats allocator library or memory allocator statistics library. This shows you stats about memory management, how many GC cycles, what your heap size is, et cetera, et cetera. And the second one was pprof, which is a package that allows you to visualize profile data for CPU usage, heap usage, Go routines, I think GC cycles as well in some amount of detail, blocking threads, mutex locks, et cetera. Pretty powerful as well. We mostly use it for heap usage only. So the memstats library itself exposes various stats about the system's memory usage. These are 3 stats that I found particularly helpful. We have heap objects, which is the number of allocated heap objects in total. Heap alloc, which is the number of bytes that are allocated in the heap. And heap sys, which is the total bytes obtained from the OS by your program. So any 3 of these that you can guess, if you make heap optimizations, you'll start to see improvements. If not, you'll start to see some degradations. So this is what we were using as a proxy for success, because it was hard to sort of run every single change that we wanted to try in production and actually see what the P90, P99 latency numbers look like. So we use this as a proxy to just do some offline testing and see what impact each change we were trying out actually had. So here's a quick sample program of how to use memstats. Essentially, we perform some heavy allocations, force a GC cycle, and print out some of the memstats to understand how the system performs at each stage. So in here, we were looking at heap alloc, number of heap objects, and number of GC cycles specifically. So here's kind of an idea of what it looks like. As you can see, especially between the last 2 lines, after we triggered a GC cycle, the objects on heap dropped, the number of bytes on heap dropped, num GC incremented to 1, but the heap sys is something that continuously increases because we're continuously requesting more memory from the system. And that is sort of handled by a different background thread as how memory is returned from your actual Go binary to the OS itself. So the first 2 numbers are really what we were trying to optimize for here is heap allocation and heap objects. So once we did that, that's how we were going to measure our success. Then we needed to figure out where we actually had room for improvement. And this is where we started to use pprof. So pprof is a command line tool. Essentially run it with the command shown here, go tool pprof, put in your options, point it to the server endpoint where your service is running. Sorry, one thing I missed out here is in order to use pprof when you're starting up your service, you need to register a couple of HTTP endpoints. I linked the Go docs for pprof in here, that list that shows you exactly how to do it. Essentially, there is I think it's debug/pprof endpoint that you need to register along with the pprof built-in handler. It's just 2 lines of code, and then you can access all these profiles through an HTTP call. So we were specifically looking at heap profiles. You can replace the /heap with /cpu or /go-routines, etc., to see more different details. But in particular, the options that the heap profile has available are in-use objects and allocated objects are the 2 that we really cared about, especially in-use objects. So once you run this command, it's going to download a tarball for you, and then you run the second command listed here on the bottom line, go tool pprof, whatever port you want your web visualization to run on, and the path to your profile file itself. This pulls up a little interactive web browser, which shows you a few different visualizations. One of them is this, where you can see sort of a tree form of sort of the method calls and the method calls under those methods, and exactly how many objects or whatever object whatever stat you're using here. In this case, I believe it was number of objects. And when I ran this, how many objects are being allocated by each method call. So in here, we can pretty clearly see very quickly that the new reader size method is allocating 45% of our entire heaps objects. So there may be some room for optimization there. I forget exactly where this code came from, but perhaps one optimization here might be reusing the reader rather than needing to allocate it every single time. For instance, if it's in a loop or if it's reused across different requests, you could just have the reader living on the heap long term rather than needing to allocate it for every single request over time. The other visualization that I found really helpful was this flame graph. So this is a cool little interactive flame graph. If you click on any bar, you're going to focus in on it and be able to drill deeper. Hey, I'm in a presentation. Good to see you. The width of the bar here indicates how many heap objects that specific stack allocated. So a wider call stack means there's a higher number of heap objects. The actual depth of the stack is not super meaningful. It essentially shows how many nested methods there are in there. This very clearly helped us jump to a couple of areas of optimization. So right away, we can see on the left, I don't know how zoomed in this is for you on the screen over there, but there's a pretty big chunk on the left, so we could dive in there and try to identify some areas of optimization in that call stack. pprof also has another couple of cool visualizations. This is one of them. So it pulls up, when you run the profile command to create the actual web browser, to pull up the interactive web browser, it also opens up a CLI for you. And one of the cool methods in there is you can just use list and a method name, and it'll show you line by line how many objects are allocated by each line within that method. So in here, we can take a quick look and see that on lines 237 and 241, we're allocating, this number is what, 20 million objects, 20.7 million objects on each line, which seems a little bit weird. And we can also see that this method is allocating almost 80% of our entire heap. So there's clearly some room for improvement here. And we'll come back to this in a second. So how do we actually then limit the impact of garbage collection? Since we said that the garbage collector runs slower when the number of heap objects increases, the easiest first step is to lower the number of objects on your heap. Secondly, reducing the rate of object allocation, which is going to reduce memory pressure overall, allow your system to run better, more smoothly, reduce the number of OS calls that need to be made. And the third one is you can optimize your data structures to minimize memory usage. So if your heap grows slower, there's going to be fewer number of GC cycles triggered, so on and so forth. There are other things you can do, like you can tune the aggressiveness of the garbage collector itself. In Go 1.19 now, you can set a soft memory limit that says, I only want you to trigger GC once my heap size hits a certain number. So like we said before, by default, the garbage collector triggers every time your heap increases by 100%. This sort of remediates that by saying, I only need you to run when my heap is whatever it is, like 10 gigabytes or so. which reduces the number of GC cycles that are happening in your system. But let's talk about these three specifically, because these are application-specific optimizations that you can make. So the first one is, how can you reduce the number of long-living heap objects? First off, you can create objects on demand. This is a little counterintuitive with our second point, and it's a little bit of a trade-off that you just sort of need to evaluate for your own case. But for instance, for our system, if we store some data, think of our ad system, if we need some data for every single item in a user request. So for every ad, for instance, if we store some data in memory on, what category does that ad belong to, or how many times has this ad been interacted with before? Those might be some examples of data we store on the heap. So rather than pre-computing it and storing it in a long-lived map for every single ad, we may be able to compute it on a per request basis to reduce the number of objects on the heap. So for instance, we might fetch this from an external source. We might, if it's data that is already stored in memory and then derived for every single candidate in our ad system, we can calculate it only for the ad candidates for that request. The second thing to be mindful of is when and where you're using pointers. So if you have a struct, if there are several fields in that struct, some of those fields are pointers themselves. Every single one of those additional pointers is going to be allocated as an extra, as another object on the heap. So if you have a reference to an object and that object contains further pointers, these are all considered individual objects on the heap, even if they are nested within the same object. So if you can change these nested values to be non-pointers, which may not always be possible, but if you can reduce the number of objects that the garbage collector needs to scan every time. And the tricky thing to look out for is that strings and byte arrays are treated as pointers under the hood. So if you can reduce the number of strings and byte arrays in your system or in your heap, you can also further reduce the impact of the garbage collector. So one example for us was, if you think about every single ad campaign that runs on Pinterest, the advertiser wants to specify an end time for that campaign. And we usually represent it as end time, that end time as a string, whether it's an epoch value or just a date. By converting those date strings to time.time objects instead, we actually saw a very significant reduction in the number of objects on our heap. And here's one quick example. So going back to the example we looked at before, actually, for create catalog map, which is the method we were examining. Like we said, lines 237 and 241 have 21 million objects allocated each. What stands out here is that on line 240, sorry, when we create the listing key, we're encoding the product ID and seller ID into some sort of string. So this catalog map, which I don't think is declared here actually, but essentially the key here is a string. So when we're allocating every single entry in this map, each one of those strings represents a new object, which is why we're actually allocating 21 million new objects on line 241. So instead, if we replace this with a struct key, so essentially we're no longer using a string, we're just creating a wrapper struct that stores the product ID and seller ID and using that to key our map with, we can see that the number of heap objects dropped by, let's see, we went from 105 million to 84 million, so about 20 million there. And that was a 20% reduction in our heap size right there.
Does that only work because your product ID and seller IDs are integers?
Yes, in this case, these are integers. That's right.
So you wouldn't really get
that wouldn't work.
Still strings, right? Like,
sorry, say that again?
so if they were strings, you wouldn't actually get a benefit. Like, it's not the struct part, it's the fact that you took strings out of the equation.
Exactly. Yep. Okay. The second one, I actually don't advise everyone to use, but if you can reduce the rate of allocation by utilizing object pooling, it can sometimes be helpful. This is typically only helpful if you see that your program tends to create a large number of short-lived objects in bursts. Because typically what's happening there is you're suddenly allocating a lot of memory, your heap size is going to increase a lot in that short period, and there might be a few GC cycles triggered as a result of that. Instead, if you're pooling these objects and retaining them for a longer period, for a longer scope, you're not seeing that heap size, increase by 100% more frequently. It's sort of a more constant, consistent heap size. The downside of object pooling is that it can very easily cause memory leaks if you're not completely safe in how you're handling those objects. So, for example, pooled objects are not garbage collected until the pool itself is manually cleared. That's the whole point. So if you continue to create new objects in the pool rather than reusing the existing ones, it may cause your application to crash due to out-of-memory errors. And secondly, there may be data leaks as well. So for instance, in our system, like we said, we have these user objects that store a bunch of information about the user. Some examples may be the user ID, user email address, user's IP address, et cetera, et cetera. And we may log those user objects to various Kafka topics or generally debug logs. If you don't properly sanitize those objects before returning them to the pool, some of that user data may persist beyond its intended scope and leak to other scopes. So for instance, we may have a user object that was allocated for user ID 1 with their IP address, and now we're suddenly reusing it for user ID 7, and we're logging some other user's IP address for a totally different user. That example may not be the best one, but I'm sure you can see how that could lead to some sort of legal issues, privacy issues, et cetera. So for that reason, I think object pooling is something to stay away from until you're absolutely sure you need it. But it can be a good way to tame your system's bursts of memory allocation. And then finally, something that I found really interesting, a couple of learnings here. So basic types in Go have default values. That's probably not news, but those default values also need memory. So for instance, in our bad object on the left here, fields I through L are unused, but since they are basic types, they all have default values. So ints default to 0, bools default to false. All of that memory still needs to be stored on the heap. So by removing those unused fields that are never referenced in our code, we were able to reduce each object size from 64 to 40 bytes. And if you extrapolate that to system of interest scale, where we're dealing with millions of ads at any given point, that pretty quickly adds up to very significant savings. The other great side benefit is the code became significantly easier to read because now people don't need to wonder what all these unused fields are for, whether they're still in use, et cetera. So it's good code practice too. One call out is it's extremely painful to figure out whether a field is used or not without some sort of, we didn't have any good static code analysis tools at least. I'm not aware of any that exist open source. If you are, I'd love to hear about them. But essentially for like 3 weeks, I was in my IDE, right-clicking on every single field, looking at find usages to figure out if this field is used or not. Not the best 3 weeks of my life, but paid off. The next one that I found really interesting, not coming from a C++ background, folks who are coming from that sort of a background, I think this is a little more obvious, but the Go memory allocator does not optimize its allocation for data alignment. So once again, in this case, well, actually, this is a little new. So bad object and good object in this case actually have the exact same fields. They're just ordered differently. Each object is allocated one field at a time. So in order to respect word alignment, the Go allocator needs to add padding to the data for the bad object. So just going through, field A is a Boolean. We allocate 1 byte for that. Field B is an int64. We need to allocate 8 bytes for that. However, if we just allocated 8 bytes after that, we would break the word alignment of the system. So the memory allocator allocates 7 empty bytes and then allocates B on the next line. This means those are 7 basically wasted bytes, which are still adding to your system's memory usage. So by just reordering our fields here, we were able to go from 40 bytes to 24 bytes again and lower the memory usage by a further 40%. So just by these two very simple changes, we went from an object of 64 bytes to 24 bytes, which in this case is a 62% improvement. Obviously, that's very dependent on your system, but once again, in a large-scale system, this sort of very simple realignment and cleanup can actually lead to significant performance gains. So that's what I have for today. In conclusion, Go Garbage Collector is extremely powerful. The benefits are that it is automated, it is concurrent, it tries its best to minimize its impact on your system. However, when you get to a very large-scale system, it is not perfect, and you may need to revisit how your system works, how your application works. And then lately, you may also be able to tune some of the knobs that the Go team has made available to influence the garbage collector's aggressiveness and optimize your system's performance. Go does give you some really cool built-in tools to debug GC problems. So memstats, pprof are a couple of them. I'm sure there's more, and I know that the Go team is working on putting together more documentation about how the garbage collector itself works. I'm not sure if they'll include specific steps in how you might go about debugging performance issues, if that's sort of beyond what they want to provide. But if they do, that would be another great resource that would make this knowledge like more accessible and more easily usable by people of all sort of knowledge levels. And then finally, in our case, we did find that very simple infra optimizations can actually have very, very significant performance improvements and even top-line metrics gain. So as a result of this, we saw latency drop by, I want to say about 80 to 90 milliseconds out of a 300 millisecond system by the time we launched. We saw several $1 million in infra cost savings. And we actually saw improvements in revenue, click-through rate from users, user engagement rates, et cetera. So for folks who work in infra teams, it's really cool to have an infra optimization actually lead to business metric movements. So it's a really cool problem to solve. And thanks for hearing me out. If you have any questions, happy to take them now or happy to take them offline as well. Drop in my email here if you want to reach out.
I'll go first if nobody else has stuff. You mentioned, and this has been a bugaboo for me here lately, that returning memory back to the OS was a different thing, right? That other, you had the line of your mem stats being printed. Mine, and this is just my ignorance. It seems like I looked into this a few months ago, and my takeaway was that Go doesn't return the memory to the OS. But then I learned later I'm wrong. Like, I'm hoping you have like the clear insight. Like, does Go actually give the memory back to the OS? And like, do you have insight on that process and kind of how that works?
That's a good question. I do not, but I'm happy to follow up with you on that one.
Okay, yeah. Like I said, I've had conflicting information, so.
I'm curious, do you have any regression testing now, knowing that this had such an impact on your system? Are you using metrics to monitor it and make sure it doesn't go back? Are you using Go benchmark to have like unit tests with allocation counts, anything like that?
I wish I could say we're not. What we do have is more rigorous latency monitoring, which we didn't have before. We would sort of do it on a per feature launch basis. The good news is that Pinterest overall is building in some profiling tools that are applicable to different languages. I'm assuming Pinterest uses AWS pretty heavily. I'm assuming it's built on the AWS stack, but essentially any user can configure their system, whether it's in Go, Python, Java, to run a CPU profile, run a heap profile, and even diff the flame graphs between two commits to sort of see the difference and see where a regression might have occurred. So that's something I'm excited to adopt, but we don't have it right now. The other fun fact is that we're actually rewriting the system in Java right now, and that's a whole other topic that I could spend hours talking about. But
Time to find a new job.
I know.
So
Well,
I'm wondering,
wondering.
I'm a little curious. You mentioned that there are lots of teams that use languages other than Go.
Mhm.
Have other teams at Pinterest experienced garbage collection issues, and like, what could you leverage any of the learnings from there? Like, what's the difference in the experience of a Java memory issue, garbage collection issue versus a Go garbage collection issue?
Yeah, I mean, historically, my team itself did. So this system was written before I actually got here, but I know that the team did evaluate Java, I want to say Elixir, perhaps, Python and Go, all as options to write this ad server in. And I think the conclusion was that, well, Elixir just wasn't supported by the company. Python and Java had significantly worse performance at that point. I think we were trying it in Java, I want to say Java 8, maybe at that point, or even Java 7. I think the biggest finding was that at that point, the Java garbage collector wasn't running concurrently, so it did introduce stop the world pauses, which at a P99 level and even P95 level, I think, was leading to enough of a regression that it was actually showing pretty poor user performance metrics. I think we were pretty early on. That was like when we first started to monetize, so we didn't really have much of a baseline to compare it to. But the team at that point deemed that performance regression was sort of unacceptable. I think what we did have is, since ads are obviously part of the main request path, because some of these P90 requests were so slow, we did see a drop in regular user engagement besides ads on the actual just organic content on the page. My most recent understanding is that after Java 14, I think they introduced ZGC, which is a concurrent garbage collector, and allows a lot more knobs to tune. So I'm thinking things like soft memory limit that Go now has, aggressiveness, perhaps even the number of cores that the garbage collector is allowed to use. which make it so that one, it is in general a more performant garbage collector itself. And secondly, you're able to tune it way more based on your application requirements. One interesting thing I did learn recently, and I'm assuming this is actually probably also the case in Go, but one of our systems that is in Java tested out ZGC and saw that they had a slight latency regression in the first minute or so of the application running. My assumption is because it probably has a similar setup to Go, where GC triggers every time the heap grows by a certain amount. So in that first minute, while the heap is really sizing up, there's a lot of GC being triggered. And then once the server's warmed up and the heap has reached sort of a more critical size, a more constant size, it sort of amortizes and goes back to regular performance.
No, that's good insight. Thank you.
Anybody else? No more. Okay, well, thank you again. I really appreciate it and
Cool.
taking the time to come talk to us. And
Yeah, thanks for having me. If you do have any questions, totally happy to take them over email. And have a great rest of your night.
sounds great. We'll give you one round of applause and
Thanks so much.